Hi everybody, welcome back to Multimediale Werkzeuge, part 5. Today about audio processing. So let's start with increasing the playback speed without changing the pitch. So this is something that we already saw at the end of lecture 4a. We saw that we can have a filter bank structure where the filter bank basically keeps the subbands in the right frequency. And we can use that for changing the playback speed without changing the pitch by changing the sampling rate within the subbands accordingly. So we usually have a lower sampling rate in the subbands because they are more narrow band, but then we can increase the sampling rate or decrease the sampling rate. So if we want to increase the playback speed, we need fewer samples, right? So we need to decrease the sampling rate accordingly. But what happens in the subbands if we do that? So first the downsampling case. So here we see some example spectrum. So horizontally you see the frequency, and here you can see the subband boundaries as those little stripes here. And then vertically is the amplitude. And this is basically the magnitude of the spectrum. So this might be some speech spectrum, for instance, here the fundamental. Here you can see some harmonics. It can also be a musical instrument. Just an example. So here are the subbands, and now within those subbands we want to change the sampling rate. So we use the normalized frequency, where the Nyquist frequency is either pi or 1. So subbands lose the higher frequencies after the downsampling. So when we decrease the sampling rate, that means each subband signal is rescaled to the new sampling frequency. So the upper frequency components of each subband can no longer be represented by the lower sampling frequency from the reduction. So the bandpass filters must be narrow enough, otherwise aliasing distortions would occur, right? So to start with, they need to be, for instance, half empty. The upper half, for instance, should be empty of each subband. Then we can reduce the sampling rate by a factor of 2, for instance, and still have no aliasing. So in this way, we need gaps in the spectrum, which means parts of the original that are not kept by the structure. Well, we lose information, right? And then this shows up as those gaps in the spectrum or in the filter bank. And we should choose the structure or the filter bandwidth so that the gaps become as unnoticeable as possible to the ear. And this needs psychoacoustics, right? We need to make use of psychoacoustic properties, meaning the masking effects of the ear. So the masking effects work particularly well with narrowband filters. So that's why many subbands are good, such as the typical number of subbands in audio coding, which is 1024 subbands. So here's an example. We have a filter bandwidth of 22 Hz, and we have a sampling rate of 88 Hz. And this is actually twice as much as we need, right? We just would need 44. So assume the distance of the subbands center to center is now 44 Hz, right? That means we only use half of the available spectrum. Otherwise, the distance would be 22 Hz. So that means we now can downsample the subbands by a maximum factor of 2 without causing aliasing. So we keep those spectral gaps to start with, and that leaves us room to reduce the sampling rate in all the subbands without overlapping of alias components, or without overlapping of spectral copies, or which then would cause aliasing artifacts. Then The second part would be decreasing of the playing speed without changing the pitch. So this is the opposite. Here we would do upsampling. That means we increase the number of samples because now they have to be sufficient for a longer time. So again, we have our audio spectrum. Horizontally is the frequency, the normalized frequency. So this is before upsampling. And then after upsampling, basically each subband now becomes wider. So if we increase the sampling rate, we now have more space on each subband to accommodate more frequencies, right? So we basically get more room in this way. And again, we will get now gaps, but now after the upsampling, we get gaps. So for the downsampling, we need to make gaps before we do the downsampling, and here they appear after upsampling. So here's an example. We have a music signal with 22 kilohertz bandwidth to start with, and this needs 44.1 kilohertz sampling rate. So here are the samples, and here the recording spectrum. So we have our audio signal, which goes up to 22 kilohertz, and this is our sampling rate, which is larger than twice the highest frequency in our signal. So this is the corresponding spectrum after normalization. So this one would be, for instance, our normalized frequency for Nyquist. So actually this normalization, I just mentioned, one would be the sampling frequency. Most often 2 pi is the sampling frequency for the normalization, and then the Nyquist frequency would be pi. So instead of a 1, we would have a pi here. So what happens if the sampling rate is increased to 88.2 kilohertz by inserting a 0 after each sampled value? Because then we double the sampling rate, right? Because we have sample 0, sample 0. So we go from 44.1 to 88.2. Then this is the effect. After inserting the zeros, we basically now have a different normalized frequency. So what was 1 before? So here, this is the new Nyquist frequency now, which is twice as high, and that means the old Nyquist frequency now becomes 0.5 for the new normalized frequency. And we get this new space in the spectrum, and this new space in spectrum is filled up with a spectral copy. So you can see this is a mirrored copy of the original, and this might cause trouble. So this could result in audible or aliasing artifacts. So we need to apply a low pass filter here to get rid of it, right? And we can do that because there's no overlap, right? If there would be overlap, then we are lost, right? But since there's no overlap, we can remove this spectral copy by using a low pass filter, which just attenuates it. So here's the new normalized frequency, and the same can be done in the subbands, right? Here in the subbands now we have a bandwidth of 22 Hertz. Remember, we have about 1000 subbands. So here's 22 Hertz in each subband, and that means the sampling rate of only 44 Hertz is enough according to Nyquist. And now we increase the sampling rate by a factor of 2, for instance, to 88 Hertz. And this produces more frequency space. So here we see it. This was before, and this is after. Here we have now the new normalized frequency, and here we have this new space, which is kept free by using the low pass filter. And basically we have the same problem as with downsampling. The spectral gaps must be not noticeable to the ear, right? So again, we use psychoacoustic masking effects. If those gaps are small enough, narrow enough, then the ear won't notice. So that means we need to use a high number of subbands. But note, a high number of subbands leads to lower time resolution because we have narrow subbands. Narrow subbands means a low sampling rate. Low sampling rate means low time resolution. Right. Too low time resolution would lead to distortions again after a modification, like the sampling rate change, for fast changing signals. Right, like when you have an attack of, say, a drum or castanet, then long filters would cause audible noises before or after this click. Yeah, so that means the time resolution must be adapted to the signal structure in general and assumptions about the signal, how stationary the signal is, which means we cannot really have too high number of subbands. In general, we need a good compromise. So we need a suitable compromise between the highest possible frequency resolution, bandwidth, the number of filters, and the highest possible time resolution, the sampling rate. What's often done is to use no critical sampling in the subbands, according to Nyquist, but a higher sampling rate. So this also gives us more room in the subbands. This can increase the time resolution a little, but only within limits, because the impulse responses of the filters also have a length of this order of magnitude. So the more narrow the filters are, the longer the impulse responses become. And that might cause smearing across attacks. So this gives increased computational complexity, but indeed often gives better results. Yeah, and then there is the possibility of changing the pitch, now without changing the playback speed, right? So different change. So there's also a demo with Audacity, which uses change pitch and change tempo, which I will show in a moment. And we use the same structure, the filter bank. The idea is to move each subband signal in the synthesis part to one subband up in the analysis part. And the result is a frequency offset, a constant frequency offset. So here's the analysis. So subband 1 will be given to synthesis subband 2 and so on. So always one up. So move each up. Right, but how does it sound? Well, the answer is it sounds artificial because the harmonic structure is destroyed. Harmonics are no longer a multiple of the fundamental frequencies, and this sounds artificial. So an example would be the so-called single sideband modulation in voice radio, for instance marine radio, amateur radio on shortwave, with a slightly detuned receiver. When we have a detuned receiver, we get a constant frequency offset, which has exactly this effect. So it sounds artificial. So a better approach is to multiply frequency components by a certain factor in frequency. So for instance, map subband 1 to subband 2, subband 2 to subband 4, and so on. So here we have a constant factor. So this keeps the harmonic structure more or less. But the problem, I guess, again, is we have gaps in the spectrum. And those gaps, they increase to high frequencies. They become ever larger. But what helps us here is that psychoacoustic occlusion effects become also wider towards high frequencies. So at higher frequencies, we can afford wider gaps because our ear filters also become wider. And for the reduction of pitch, we basically have parts of the spectrum which disappear accordingly. Yeah, then finally we have a notch filter. A notch filter is also quite practical. For instance, if you want to suppress a certain frequency, for instance, unwanted 50 Hertz humming frequency. So this is often when you have like bad microphone connections, then you get 50 Hertz humming from the environment. So in Europe it's 50 Hertz power frequency, and in Americas it's 60 Hertz. So there you would need a notch filter for 60 Hertz. So a notch filter basically passes all the frequencies except this one frequency. And we could use a DFT as the notch filter, basically apply a DFT transform to our entire signal and then just set the according subband for 50 Hertz to 0. But that doesn't really work because it turns out the DFT is a bad filter bank, which doesn't give you enough attenuation. So that means it's not really working for removing the unwanted frequency. So the better approach is to use a real notch filter, which gives you, for instance, 40 dB attenuation, realized as FRR or IIR filter. Yeah, so this can remove this 50 Hertz humming from a signal. It leaves only a narrow gap. So again, this narrow gap is important because then it's inaudible. So the 50 Hertz is gone, but since the gap is very tiny, then it's not, the ear doesn't notice that something is missing. Right, so it should be inaudible. So that's why it's important that the gap is narrow. But if we switch this tone on and off, which for 50 Hertz we don't do, but for other frequencies we might, there can be a residual hum at the beginning and end of the signal because of oscillations of the filter. Right. Yeah, so at this point, let's try this demo using Audacity. So I have a little demo here. Right, so ls star.wav. Let's see what I have. Nothing. Okay. Oh yeah, it's not WAV, it's a different format. It's MP3. So here we see it. For instance, Beethoven's Symphony, right-click, open with Audacity. So Audacity is open source, so you can freely download it from the internet, and it's actually quite powerful. So, okay, so here you can now see Audacity, and you can see the two tracks from this stereo recording of this classical piece. So I can start playing it back. So this is how it sounds like. And now we can apply those processing steps that we just heard about. So I mark a piece of the music like this, and then I can say effect. And here we have, say, change speed. So now I want to make it faster, so I have a factor here of, I can use the slider here. For instance, I can use a factor of 1.5. So that means I reduce the sampling rate in the subbands by this factor of 1.5. So I can say OK. Now it already is done, and now let's play it again. Yeah, so you could hear that it's indeed much faster, and the pitch should be about the same, right? So at least it was not noticeable that there was a pitch change. So then I can do undo, and now I can apply the opposite effect, change speed. I can make it slower, say a factor of 0.7. So now we upsample by a factor of 1 divided by 0.7. So we can see here, now we get more samples. It becomes wider. And I can play it back. Yeah, so we could hear that it's really noticeably slower than before. So I can say undo again. And now we can apply the pitch change. So change pitch. So here we have again a slider. So this is unchanged. 0 is unchanged. So let's make the pitch higher. So let's say factor of 2, 100% higher. Okay. And now we can play it back. Yeah, so you could hear it was really a lot higher, but you could also hear artifacts, right? Those artifacts that I mentioned. So this is a little bit too much for this approach. So let's see, undo. And now I can do the same in the opposite direction. Change speed. No, I wanted to do change pitch. Effects, change pitch. So now let's go to 50%. Okay. Now let's try again. Yeah, so now you could hear it's indeed much lower, so about 50% lower than before. And actually in this case we could hear fewer artifacts. Okay, so right, notch filter. So we don't really have humming on it, so we could add a tone. For that we first add a new track, add new stereo track, right? And then we can generate a tone. So here, generate tone. We take a sine wave, sine tone 440 Hertz, amplitude 0.2. So, okay. Oh, I didn't want it there. Undo tone. So I point the pointer here in the beginning. So add tone, generate tone. Okay, so now we have the tone in the beginning, and now we can mix the two signals, the tone and the music. I can just mark everything like I did here, and then I say tracks mix. So mix and render keeps them in the same tracks. So here I now combine the two. So here you can see now I have the music plus the tone, and that sounds bad. So we can listen to it. So indeed it doesn't sound good. So this is an artifact that we now want to remove. And for that I can again mark it, and then I can apply effects. And here the notch filter that I now need to use is can be found here in plugin 1 to 15. So it's a little bit hidden on this practical tool, but here 1 to 15 leads me to this notch filter here, right? So here you can see it, notch filter, it's preset with 60 Hertz, which is the power frequency in the Americas. But now I'm having 440 Hertz. So 440, and I can say here Q value. Yeah, this Q value gives me the attenuation and the width for the notch. Let's see if 1 is sufficient. So, interesting. So let's see what happened. It's actually not bad. So the tone is basically completely gone, but the music maybe changed a little. So when I say undo notch, you can also try it with a different notch filter. Effect, plugin 1 to 15, notch filter, and maybe increase the Q value to somewhat higher. Let's say somehow it doesn't really want to change. Interesting. 10. It's not. God. It's not doing what I want. So effect, plugin, notch filter 10. Let's see how that worked. Yeah, so we could hear in the beginning there was a short beep from the tone left because the filter started a little later. And then the signal is basically undisturbed here. So the Q value of 10 gives us a more narrow band notch. The higher the Q, the more narrow the notch will be, and the more it leaves of the rest of the signal. So 10 seems to be a good value here. Okay, so that works nicely. So next, noise reduction. This is also something that can be done in the subbands. So we can take our audio signal, again decompose it into our subbands, do downsampling more or less, and then we apply a thresholding here before we give the signal to the synthesis filter with upsampling and filtering again. Right, and this is the nonlinearity, and this means that the input signal needs to reach a certain amplitude before it is passed to the output. You could think about this as a switch, and this switch only turns on when the signal reaches a certain level. Right, so the goal here is to have noise below the threshold. So that means if you have a low level in the subband, then you assume that it's noise, and then you keep it zero, right? Basically you set that subband to 0, which you assume is noise. Yeah, and that also means to set the threshold correctly, we need an estimation of the noise power, right? A precise estimation. Yeah, so the effect is the signals of the subbands in which only noise is present are set to 0. This removes the noise then. We have a reduction of the noise power without reducing the desired signal. Right? So this is an effect like selective filtering, which means attenuation of parts of the spectrum where the signal to noise ratio is low. And the effect is similar to the so-called Wiener filter, which is an approach to minimize interference or noise by maximizing the signal to noise ratio. Assumption here is that the noise is relatively constant across frequency, and the desired signal is located in relatively compact frequency blocks, for instance, harmonic structures of music or speech. In this way, some separation of noise and the desired signal is possible. Yeah, we can do something similar also for images. There we would also apply a subband decomposition, but a different type. For instance, a DCT of type 2 or wavelets, and this subband decomposition is then done over space and not time, right? So we have spatial subbands. And the nonlinearity looks a little different that is usually used. So instead of using just a switch, we shift the output also a little bit down. So when basically this on switch also reduces the output accordingly here. So there's no step anymore. Yeah, and this is used in image denoising. So the DCT is usually used for JPEG compression to basically ignore high fine details in images. And you can do the same for denoising. So when you have noise on images, it often appears as like the snow pattern, so it's often fine details. And then this nonlinearity again helps to remove those subbands which only have the noise patterns in them. So it smoothes more or less the image. Yeah, and finally stereo modification. So we can also do this in Audition or Audacity. So Audition is from Adobe and Audacity is open source. So here we can convert from left-right to mid-side. Right, and this is usually done for stereo coding. Instead of having two separate left-right channels, you compute the mid by averaging and the side by taking the difference. And for instance, when you have a 400 Hz sine wave identical on the left and right channel, then after the mid-side transformation, only the mid channel is left and the side channel contains only zeros. Or you could also have, say, speech, when you have news on broadcast radio, for instance. Usually you have music in stereo, but then you have news, and the speaker is usually right in the center, which means you have the same signal on the left and the right channel. And that means when you do the mid-side coding, you would get the signal, the speaker in the mid channel, and the side channel would be empty. So that could be encoded with very low bit rate. So that's advantageous for coding. Yeah, okay. So that should be it for today. Thank you for your attention and see you next time.